Okay. Uh, Hello, everyone. Check. Recording in progress. Hello, everyone. Can you hear me? Okay. Good morning from Shanghai. I'm Zhiwei Wang from Tongji University. And today I will talk about creating artificial nanochannels in thin film nanocomposite polyamide membranes for efficient removal of trace organic contaminants. I'll cover the following several aspects. First of all, it's a background information. I think everyone knows that wastewater reclamation is of great importance for constructing a sustainable urban water system. A lot of technologies can achieve the wastewater treatment and reclamation. Among those technologies, membrane separation technology has attracted much interest in recent years due to the following advantages, such as no phase change, highly efficient solid liquid separation of the pollutant water separation, and also adjustable selectivity and so on and so forth. However, we all know that there are a group of contaminants. We call that trace organic contaminants. It's still a big challenge. It will exert huge impacts on ecosystem, even at trace concentration. It will also attack human reproductive and immune system and so on and so forth. So we need to develop countermeasures to remove such kind of pollutants. For instance, polyamide nanofiltration membranes is a promising technology to deal with such kind of pollutants. However, for traditional polyamide nanofiltration membranes, it was not designed for removing such kind of trace organic contaminants. So for instance, the polyamide membrane is usually negatively charged. So this kind of membrane surfaces will cause poor rejection of positively charged pharmaceuticals. Also, the interaction between the polyamide surface and the pollutants, such as the hydrophobic interaction, also will cause the absorption of the EDCs and thus a poor rejection of these pollutants. So we need to develop such, develop methods to modify the nanofiltration membranes for enhancing the removal of trace organic contaminants. So in literature, there have been several methods to further enhance the rejection of trace organic contaminants, such as polydopamine coating, and also the tannic acid ion coating, and also polyzetol and layer by layer coating and so on. However, for those methods, it will compromise the water permeability, even though it could enhance the rejection of trace organic contaminants. So how to deal with such issues? So we are thinking about the metal organic frameworks. So, for metal organic frameworks, it has several advantages, such as, it's usually highly porous and also has adjustable process and easy post-modification. So we aim to construct artificial nanochannels in polyamide, active layer to selectively remove those trace organic contaminants. So the first part, we construct a hydrophilic selective MOF nanochannel for EDCs removal in the nanofiltration membranes. So first we prepared the MOF materials. It's a MIL 101. It's a kind of a chromium based MOF materials. So we, after preparation of the materials, we use SEM, XRD, FTIR to characterize the MOF materials. And the results showed that, we successfully synthesize such kind of hydrophilic MU101 MOF particles with a pore openings about 1.2 and 1.6 nanometers. Then we incorporated the MOF materials into the polyamide active layer. We, during interfacial polymerization, we just, put the MOF particles, with a predetermined dosage into the TMC hexene, and use interfacial polymerization. We could incorporate the MOF particles into the PA active layer. We use TM, XPS, and ATR, FTIR to characterize the modified membrane. And you could see here, the MOF particles were embedded into the PA active layer. After this, we are, very interested in the performance of the MOF TFN membranes. Here you can see that after incorporation of the MOF particles compared to the control, the rejection of 4 EDCs were increased. However, if you further increased your MOF dosage, such as 0.25%, it will cause a decrease in the rejection of those EDCs. So we further calculated the A over B ratio. It's called water and EDC selectivity. It shows a similar trend with the rejection performance. And then we are wondering, the mechanisms lying behind. So we conducted a sorption test using this modified membrane. You can see from this figure, the sorption of EDCs after the incorporation of MOFs, it shows a decreased trend, suggesting that, after incorporation of the MOF particles, the sorption of EDCs to the membranes were inhibited. So, as we all know that, for the rejection of trace organic contaminants, sorption is a first step. If you can decrease the sorption, the rejection of the EDCs would be increased. So that's why our membrane could achieve a high rejection of those trace organic contaminants. Then we further validated our hypothesis. We detected the water contact angle here. You can see here for an F control, the water contact angle was about 52. And after incorporation of the MOF particles, the water contact angle of the membranes decreased gradually, from 52 to 31.8 degree. It clearly showed that the incorporation of the MOF particles could increase the hydrophilicity of the polyamide membrane. Also, for clarifying the mechanisms, we also use some single salts, such as sodium chloride, calcium chloride, and sodium sulfate to detect them, to clarify the major mechanisms. Here you can see, for the sodium chloride rejection, after we incorporated the incorporation of the MOF particles, the rejection of sodium chloride, shows a slight decrease. It means, the rejection of the sodium chloride was decreased. However, very interesting. It's very interesting to notice that, for the calcium chloride, you can see here after incorporation of the MOF particles, the rejection of the calcium chloride increased. It suggests that, after incorporation the MOF particles, the rejection of calcium really increased. It suggests that, the MOF particles played a dominant role in rejecting such kind of salts, suggesting that, the nanochannels will also play a dominant role in rejection of the trace organic contaminants. Also, why it will cause such kind of change. Here, we show the zeta potential of the MOF particles. You can see here, the zeta potential of the MOF particles are higher than the membranes. So if we incorporated the MOF particles into the polyamide membrane, it will, how to say that? It will, decrease the negatively zeta potential, so it means the repulsion of the polyamide membrane with the negatively charged pollutants will be decreased. So that's why, for calcium chloride, due to the presence of calcium, so the repulsion of calcium and the polyamide membrane will be increased. However, for the sodium, sodium sulfate, it's kind of, it was mainly dependent on the sulfate ion for the rejection ratio. So for the sodium sulfate, due to the inhibition of the repulsion of the polyamide membrane with the negatively charged ion, so it shows a decreased trend compared to the control. So through this test, we could see that the nanochannels we created really played a dominant role in mass transport in the nanofiltration membranes. Also, here we show the pure water permeability of the prepared membrane. You can see here, compared to the control, after the incorporation of the MOF particles, the membrane, the water permeability increased. Further, we use the gold nanoparticles to indicate the filtration phenomenon. Here, for the NF control, it means without MOF particles, the gold nanoparticles were distributed evenly on the nanofiltration membrane surface. However, after the incorporation of MOF particles, you can see here during the filtration, the gold nanoparticles were clustered around the MOF particles, suggesting that the channels, the nanochannels of the MOF particles played a dominant role during filtration, causing the accumulation of the gold nanoparticles around the MOF particles. Yeah, it clearly shows that there were nanochannels that we created in the nanofiltration membranes. Then we proposed such kind of mechanism for the enhanced rejection of the trace organic contaminants. For traditional nanofiltration membranes here, the hydrophobic EDCs will first, it will, adsorb on the PA active layer. After sorption, the adsorbed EDCs will transport through the PA membrane into the effluent. So it causes a not very good rejection of the EDCs. For our modified membrane here, we incorporated the MOF particles into the PA active layer. So there was water channels in the MOF particles. So also, the nanochannels is hydrophilic. However, the EDCs are hydrophobic. So during the transport of water through the nanochannels during membrane filtration, the hydrophilic EDCs will be rejected. So it will induce the increase of the rejection ratio of the hydrophobic EDCs. Also, you will care about the membrane stability of the MOF modified nanofiltration membranes. So we just carried out the soaking and leaching test for 14 days. And when we found that no chromium element was detected during 14-day leaching test for the MOF modified membrane. Also, we conducted the toxicity test of the leaching supernatants. Here we found that the supernatants did not show significant toxicity on the luminescent bacteria. It's again suggests that the membrane has a strong stability during long-term use. So the second part, we want to further modify the selective MOF nanochannels for charged pharmaceutical removal. As I mentioned earlier, the MOF particles has a kind of nanochannels. So on the outside, it has abundant capsule groups. So it will be negatively charged at neutral pH conditions. So we are thinking about, it's outside is negatively charged. How to, further modify the nanochannels to, increase the rejection of the positively charged pharmaceuticals. As we all know that if it's negatively charged, the rejection of positively charged pharmaceuticals will be decreased. Then we are thinking about, we want to modify the nanochannels on the chromium coordinated unsaturated metal sites here. If we could immobilize a mine group here onto the CUS, it will, for the internal nanochannels, will be positively charged. So through this way, we can also increase the rejection of positively charged pharmaceuticals. So, after this, we prepared, the other two MOF particles. We just modify the MOF particles with the ED. Yeah, we modify the mine group onto the CUS of the MOF particles. And for the third one, we just use a kind of a sulfonic acid group to graft onto the CUS. And it's kind of a sulfonic group. It means it will be more negatively charged. So it's there will be three kinds of MOF particles. Then similarly, we incorporated the three MOF particles into the PA membrane. It's a NF control, and it's a mu TFN, it's a mu 101, and also ED modified TFN. It's will be positively charged for the internal channels, and also the sulfonylic modified TFN membranes. It will be more negatively charged. So there will be four membranes. And then first we used the golden nanoparticles to observe the kind of nanochannels for water transport. Here for the NF control, similarly, you can see that the golden nanoparticles will evenly distribute onto the membrane surfaces. For the EDTFN and the MU-TFN and the AMSA-TFN, you can see the golden nanoparticles were clustered around the MOF particles. And then let's look at the pure water permeance. You can see here, after the incorporation of the MOF particles, three kinds of MOF particles, the water permeance, all of them increased. And then we took a look at the rejection for the, here is calcium. You can see here for the EDTFN, it means the internal pulse was further modified with a mine group. The rejection of calcium increased dramatically compared to the control. However, for the AMSA-TFN, it's kind of sulfonic group modified membrane. The rejection of calcium chloride was decreased. It shows that after the incorporation of the MOF particles, it clearly dominated the water transport and mass transport of the modified nanofiltration membranes. Then we examined their performance in rejection of the charged pharmaceuticals. Here you can see that for the positive charged pharmaceuticals, the EDTFN achieved a higher rejection compared to the rest nanofiltration membranes. Yeah, it again confirmed our hypothesis. We further calculated the A/B ratio. A similar trend can be observed here. We further use a molecular simulation to detect the mechanisms. We found that the carboxyl groups outside the mouth show higher repulsion energy to the negatively charged pharmaceuticals than the amine group inside the pulse. And the primary contributor to the repulsion, between the positively charged pharmaceuticals and the membranes is a amine group. So clearly, confirming our hypothesis. Then the last part I want to briefly introduce, there will be kind of transition of the primary selective nanochannels in MOF-TFNF membranes. Here, I will skip this. Here we just, use different PIP dosages from C1 to C4. If we increase the PIP dosages, the cross-linking degree will be increased as well. Here you can see this, if you use PIP a higher PIP dosage, the cross-linking degree will be increased. So we just show you here, if you use a lower PIP dosage, the water will not only pass through the PA active layer, but also the nano pulse of the our created nanochannels. However, if you further increase the cross-linking degree, then gradually here you can find that you could control the water just transport through the nanochannels that you created in the nanofiltration membrane. So through this way, we could achieve the rejection of trace organic contaminants, since we could modify the nanochannels of the artificial ones. So that's the main idea. Then we carried out a lot of experiments to confirm the transition of the primary nanochannels from the PA layer to the artificial nanochannels. Due to time limitation, I will skip this. Then a brief summary. We designed a MOF-TFN membrane, MOF-TFN membrane for the rejection of trace organic contaminants. The rejection of hydrophilic EDCs could be enhanced via incorporation of MOFs into the PA active layer without compromising the water permeability of membrane. Also, MOFs played a dominant role in mass transport through the TFN membranes. Also, please note that the internal pulse could be modified to further optimize the rejection performance against charged pharmaceuticals. Also, there is a very interesting phenomenon. It will occur, the transition of the primary water transport nanochannels in the TFN membranes. If you increase the dosage of the monomers during interfacial polymerization. With this, I conclude my presentation. Thank you very much for your attention. Thank you. Okay, let me check whether there's any question. No question? Okay, no question. I'm also the chair of this session. So due to the schedule, I think we can move on. Okay. Oh, there's a question. We have a porous material with a pulse size around 20 micrometer. Is it possible to fill the pulse with MOF? To fill the pulse with MOF? Yeah, it depends. It means we need to develop a MOF particles with appropriate particle size. In our research, the MOF particles is about 200 nanometers. Yes, I think we can fill the pulse using this kind of MOF particles. Yeah, we need. Yeah. Any other questions? Okay, if you wanna, raise kind of questions, so you can enter the questions in Q&A. Yeah, you are right. Another question. Yes, we should control the distribution of MOF. So during the membrane preparation, during the interfacial polymerization, we use ultrasonication to distribute the MOF particles. We just put the MOF particles in the TMC hexene solution. So in that solution, we need ultrasonication to distribute the MOF particles, and then we could, proceed the interfacial polymerization process. Okay. Okay, thank you. Yeah, due to time limit, I will introduce our second speaker of this morning's session. Our second speaker is Professor or Dr. Kaifeng Gu from Zhejiang University of Technology. Today, Dr. Gu will talk about performance optimization and transfer promoting effect of polyethylene nanofiltration membrane. Okay, please join me in welcoming Dr. Kaifeng Gu. Please, Dr. Gu.
Hello, everyone. My name is Gu Kaifeng. I'm from Zhejiang University of Technology. My research topic is performance optimization and transfer promoting effect of polyethylene nanofiltration membrane. From 1959, it was first discovered that cellulose acetate membrane had a detonation effect. Thorbo and Sorogen used the phase inversion method to prepare C membranes with asymmetric structure. This asymmetric structure had a significant impact on the increase in flux. In extreme development of this resulted in the TFC membrane. In the following decades, whether the research or commercial production, the common nanofiltration membranes are usually TFC membranes. In addition to the widely used interfacial polymerization, the coating method was also an important method for preparing TFC nanofiltration membranes. The earliest TFC membrane was made from this. PEI was a common rare material for memory preparation, which prepared the first interfacial polymerization TFC memory. This polymer has many advantages in memory preparation, including extremely soluble in water, strong reactivity, great memory forming properties, and highly positively charged. So it was an ideal raw material for the preparation of positively charged non-filtration memories. Researchers have developed various methods to prepare PEI positively charged non-filtration memories and applied it in water softening, heavy metal remover, dry separation, antibiotic separation, solvent resistant, and other fields. However, these memories still have some shortcomings that limit their application. As complex memory preparation process, low permit flux, high in energy consumptions. To solve it, select the appropriate memory preparation process and optimize memory preparation parameters were effective methods to solve these problems. In our work, we propose a method for preparing gradient cross-linking transmesic acid and polyacetylenilamine non-filtration memories. The detailed discussion was carried out from the memory preparation process and the transfer process. I will introduce the whole experiment in two parts. To prepare the PI-TMA memory, we distribute the cross-linking agent solution and the PI solution on the PES memory surface. This formed an ultra-thin and smooth polymer coating. Covalent cross-linking and electrostatic combination made the composite layer structure great stability and permeability. FTIR and XPS analysis can prove this. We conduct performance testing and optimization of memory preparation parameters. Concentration and heat treatment process have a great impact on memory performance. Optimizing the properties could obtain the memory with high selectivity and permeability. The memory had high selectivity to magnesium chloride and high soda sulfate transmission rate. The highly positively charged memory surface lead to such a separation effect. We believed that the Donan effect had played a leading role in the designation process. The loose point size is not enough to hide hydration ions. The PI-TMA memory designation did not depend on point size screening. Therefore, under the condition of maintaining high designation, the loose memory points increased the permit flux. Combined with similar products, the PI-TMA memory in this work had obviously advantages in terms of basic performance, as the high rejection, the high flux, and the low operating pressure. In the process of searching PITMA members, we found that the permit flux could be further improved at filtering sodium chloride. And this growth did not come at the cost of a decline in detonation performance. In sodium chloride solution, the PITMA membrane was stable. It still has a high removal rate of magnesium chloride. In the mixed salt solution, the PITMA membrane still distinguishes magnesium ions from the sodium ions very well. We believed that this characteristic stemmed from ion hydration and membrane pore expansion. For the PITMA membrane, the sodium ion permeability was extremely high. In pure water, large and orderly clusters of water molecules were formed through hydrogen binding between water molecules. In the salt solution, the clusters of water molecules were destroyed due to the ion hydration. Water molecules wrapped on the exotic ionous surface to form a hydration layer. When the feed liquid changes from pure water to sodium chloride solution, the sodium ions that easily permeate the membrane carried a large number of water molecules for penetration. On the other hand, sodium ions expanded the membrane points. There were two forms of covalent cross-linking and electrostatic binding in the composite layer. When sodium ions permitted, the electrostatic binding state was opened under the action of electric charge. The degree of membrane pore expansion increased with the increase of sodium ion concentration. The intuitive performance was that the rejection of PEG dropped rapidly. According to further analysis of the membrane points, the probability function of the membrane pore distribution changed after filtering the sodium chloride solution. As the concentration increased, the membrane pores became larger and the distribution range became wider. Therefore, we believe that the ion hydration and the membrane pore expansion caused the increase in flux. The above was our analysis and discussion of the PITMA nanofiltration membrane. Thank you.
Okay. Okay. Thank Doug Gu for his presentation. So since I guess Doug Gu just did not present online, so we just escape the Q&As. Okay. So then let's move on to our next speaker. It's Dr. Zhenzhen Zhang from Germany. Today she will talk about a symmetric isoporous block copolymer membrane with tunable processes and functionalities for selective transport. So let's welcome Dr. Zhang. Okay, please.
I'll just share my slides.
Okay.
Do you see my slides properly?
Yes.
Okay, super, thank you. Okay, thanks for Professor Wang's introduction. I'm Jingjing Zhang, working at Institute of Memory Research here in Germany. I got my PhD here and continuously doing my postdoc research and work on some more projects about isoporous block polymer membranes. Today, I'm talking about how we could tune the pore size and pore functionality and make this type of membrane suitable for molecular separation. So first, I would like to answer why we need isoporous membrane. And as most of us already know, one of industrially important process of membrane production is non-solvent induced phase separation. Normally we call NIPS. This process is quite simple. Basically, we cast the membrane film and then put into the non-solvent bath to get those open pores structure. As we know, we use those membranes can separate the molecules and particles with large size difference, but cannot separate substances with similar size or even with small size difference. So this is because of broad pore size distribution. This is the reason for us to searching for isoporous membrane. One way to produce the isoporous membrane is a combination of self-assembly of block polymer and industrial NIPS process. Normally, we call NIPS process. So what does it exactly happen during NIPS process to produce such beautiful isoporous membrane? So like this cartoon shows, for example, AB diblock copolymer. For SNIPS, the general casting procedure is similar to NIPS process. First, we cast the block polymer solution, and then the volatile solvent evaporates. This makes the red chain A block separate from the blue chain of B block and form those cylinders with the swollen blue chain of B block. Those cylinders are perpendicular to the membrane film surface. And afterwards, we put this membrane film into the non-solvent bath. This swollen blue chain of B block collapse and to form those uniform open pores. So this is basically how we could get the isoporous membrane. So when we talk about one type of membrane, basically there are two major issues. One is tuning pore size, another one is tuning pore functionality. So for us, in our case, also we are focusing on those two issues. The pore size of most block polymer membranes in the ultrafiltration range. So it's very important to tune the pore size from ultrafiltration to nanofiltration. As we already saw in the last slide, the open nanochannels are produced by collapsing those swollen microdomains during phase inversion. When we think about tuning the pore size, if we can use the reverse process to do the tuning of the pore size, it means we can make the collapsed polymer chain along the open nanochannels to swell or expand to reduce the pore size. For this, we know the polyelectrolytes can dissociate and then swell or expand their chain to reduce the internal electrostatic repulsion. Based on those, we can post-modify the polymer chain within the pore nanochannels to introduce the polyelectrolytes and then tune the pore size. In the meantime, we also introduce the charged functionality. Based on this idea, our first study is to use the polystyrene block polyphenylpyridine membrane. Here we call PSP4EP membrane. And we post-modified the performing block P4VP with alkyl halides. Afterwards, we got the positively charged membrane. This membrane has reduced the pore size from ultrafiltration to nanofiltration. To tune the pore size in a wide range, one hand we tuned the length of the alkyl groups. On the other hand, we tuned the degree of the functionalization. So in this study, we used the P4P or pyridine functional groups within the nanochannels. We were thinking if we can introduce two functional groups within the same nanochannels, like this cartoon shows, and then we have more opportunities to for further post-modification. For this, we present the approach to bottom-up design and synthesize the ABC trilocal polymer with two different functional groups, exactly hydroxyl group and pyridine groups. Afterwards, we produce the isoporous membrane by SNPs. And furthermore, we decorate the nanochannels with positive charge and negative charge through different post-modification methods. So now we were wondering where we could use those type of membrane. And here is showing their, it's showing their separation performance. First is about positively charged membrane, MM. We used two molecules with similar size, around 1 nanometer, but different charge. One is the cationic molecules, another one is neutral one. And the feed mixture solution is this color. After passing through the positively charged membrane, it turned into yellowish color. This color is exactly from the neutral molecules. It means the membrane can highly reject the cationic molecules and allow the free pass of the neutral molecules. So here is the negatively charged membrane PM. Similarly, we use two molecules, but with different size, also different charge number. And one is the smaller monovalent molecules. Another one is the larger trivalent molecules. The feed mixture solution is this yellowish green color. After passing through the negatively charged membrane, we see the color turn into orange color. This is from the smaller monovalent molecules. It means the large trivalent molecules was highly rejected, and the membrane allows the pass off for smaller monovalent molecules. So based on those, we got very exciting separation performance. But one thing we need to mention here is the permeance through those membrane is still in the typical nanofiltration range, around 10 to 15 liter per square meter per hours per bar. So we were wondering if we can control the swelling of the polymer chain in the nanochannels, and then to improve the permeance of the membrane, but not lose the selectivity much. For this, we present the approach to bottom-up design the performing block with randomly distributed hydrophobic unit and hydrophilic units. Afterwards, we produced the isoporous membrane where SNPs with the assistance of the titanium dioxide nanoparticles. And furthermore, we post-modified the nanochannels by sulfonation and introduced the polyelectrolytes within the nanochannels. The sulfonated membrane shows a rather high water permeance, much higher than the typical nanofiltration range membrane. And another thing is this membrane also showed a good selectivity for small molecules. And one exciting point is that this membrane has a very good antifouling property with a more than 95% flux recovery ratio after 3 hours retention measurements. So above those studies, we tuned the hypothesis together with introducing the charged functionality. We were wondering it would be more exciting if we can tune the hypothesis and also introduce the pore functionality independently. So in this work, we present the top-down process and grow the metal oxide within and onto nanochannels by atomic layer deposition, ALD. And afterwards, we introduced the different functionalities, created fluorinated, cationic, anionic functional groups along the nanochannels. This work is collaborating with Professor Sigal Peretz from Technion, Israel. And now we are wondering how about their separation performance. Here is a fluorinated membrane, and we used the 2 molecules with similar size, around 1 nanometer, but different hydrophilicity. One is hydrophilic, another one is hydrophobic. So after passing through the membrane, we can see the hydrophilic molecules was highly rejected, while the hydrophobic molecules can pass through the membrane. We got a very exciting selectivity. Here is a positively charged membrane. We used the 2 proteins molecules with different charge but similar size. One is positive charged, another one is slightly negatively charged. And from here, we can see the membrane can highly reject the positively charged protein and allow the pass of negatively charged protein. And here is showing the anionic or negatively charged membrane. And we use the different anionic molecules and with different charge number, also different size, plus 1 neutral molecules. From this graph, we can see the membrane can highly reject the larger anionic molecules with also higher charge number and allow the pass of the neutral molecules and also the smaller anionic molecules with lower charge number. So from those results, we can see our prepared functionalized membrane showed very promising results for molecular separation. So just to quickly sum up, our goal is to build up a proper membrane system for molecular separation beyond the typical size-based selectivity. We propose the 2 approaches. One is bottom-up design the architecture of the blocopolymer, and then post-modify the nanochannels with tunable pore size and charged functionality. Another approach is top-down process by growing the metal oxide within or onto the nanochannels. Afterwards, we decorate the different functionalities along the nanochannels. And from those 2 approaches, we got very promising results. So finally, I would like to thank our team from HARRY-ON, also the research team from Technin Israel. So I'm happy to take your questions and comments. Thank you very much.
Okay, thank you, Dr. Zhang. Very nice work and a very nice presentation. So I guess there is one question raised by Dr. Ma. I guess so. How about the hydrophilicity and or the capillarity of the nanochannels? I think the question is for you, Dr. Zhang.
Yeah, I mean, how about the hydrophilicity? I mean, the hydrophilicity is concerning the post-modified membrane or concerning the specific type. I can generally to answer is for like positively or negatively charged the membrane. Afterwards, the hydrophilicity does not change much. But for this metal oxide grown membrane, the hydrophilicity increased a lot. So I hope this is a proper answer. And another thing is, I'm sorry, is about, I cannot see the chatting side.
It's a capillary property.
Capillary?
Yeah, I think so.
What does that mean, the capillary? I'm sorry. Can you?
Okay, so Dr. Ma is online. Can you, explain your question, Dr. Ma?
Hello. Hey.
Yeah.
Hi.
Yeah. I mean, we know if it's a hydrophilic material, we know it has nanochannels. If there has some like a wicking effect or capillary, I mean, wicking effect. So it can absorb the water automatically into a high level. I mean,
yeah. Now I know what you mean. Yeah, it's true. If the nanochannel is rather thin, and then definitely the water can absorb into this nanochannel. But in our case, to be honest, we did not test or measure this property because in our case, we are aiming to use this membrane for liquid separation. So if the nanochannel, like our nanochannel, before modification is around 20 or 30 nanometer, after modification is around, definitely it's go to the nanofiltration range. If there's the capillary property and it's kind of advantage for our application because we want to let the water go through our membrane.
Okay, thank you, Arza.
Yeah, thank you for your question.
Okay, so any other questions? I did not see in the Q&A window. Okay, no other questions. So let's please join me in thanking Dr. Zhang once again for her nice talk. Thank you, Dr. Zhang. Thank you.
Thank you.
Okay, let's move on to our next speaker. Check my. Yeah, our next speaker is Angelo Berto Ramos from Chile. Yeah, today he will talk on new perspectives for monitoring the aquaporin biomimetic membranes fabrication per size. So, Angelo, yeah. Angelo, can you hear me?
Hi, yeah. Can you hear me too?
Yes.
Okay,
good.
Thanks.
Yeah, you can share your slides.
Okay, but I think Chen Chen is still sharing her screen.
Okay, Dao Zhang, you can, Yeah, okay.
Oh, no,
So,
no,
yeah.
now I think I can. Okay. Okay.
Yeah. Let's
Do
see
you
it.
see the screen? Okay. Ah, okay.
Yes,
Perfect.
yes, good. Yeah,
Okay. Let me put
please.
the laser. Okay. Thanks for the presentation. Well, as Wong said, I'm a PhD student from the University of Concepcion in Chile. First of all, I'm going to make a small introduction about the state of the desalination industry in Chile. Well, according to the WRA organization, Chile is the 18th country with the highest risk to suffer water stress. And due to the long coastline that the country has, it's an opportunity to use seawater as a fresh water source. However, only 1% of the total water demand comes from seawater. The industry is just emerging, but it's tending to increase. Just the copper mining industry project to double its desalination capacity in the next 10 years. In this context, my group of research at the University of Concepcion, here at the south of Santiago, the capital of the country, open an investigation line related to desalination, the installation of small nanofiltration plants for rural communities, and some membranes modifications. And in this line, we started to investigate a little bit about aquaporins biomimetic membranes. Well, aquaporins are a family of integral membrane proteins in charge of water transport across the cell membrane. This protein forms a bidirectional pore which allow the water to enter and leave the cell. This protein has a highly selective and permeable to water, and due to its outstanding inner capacities, emerged the idea to immobilize this protein into a porous substrate for water filtration. Some initial studies suggested, based on the water permeability of vesicles with aquaporins, that this membrane could achieve a permeability of around 2 orders of magnitude higher than conventional reverse osmosis membranes. This is a little bit exaggerated because it comes from a wrong extrapolation. Now, until the date, the experimental results are far from the theoretical expectations. Most of the study point to problems related to membrane stabilities or some defects in the surface of the membrane. These issues are evidently important, but there might be some other issues that might not be covered completely by previous studies. So the objective of my research and this presentation is to identify critical issues in each step of the ABM fabrication process, which could be affecting the membrane final performance. Unfortunately, due to the COVID pandemic, my investigation get a little bit retarded. So now I'm going to cover this by a bibliographic review and some experimental results that I want to show you. Well, ABM fabrication process can be summarized into 3 big steps, which are aquaporin production, aquaporin reconstitution, and immobilization. Each of these steps were well analyzed in a review article we published this year. In this presentation, I'm just going to mention some of them, but if you're interested in the topic, I invite you to read the article. Now, for the aquaporin production, it is important to keep in mind 2 concepts, which are yield of production and functionality of the protein. These 2 are dependent of multiple factors. Some of them are a little bit out of this conference, but includes the gene source, the expression vector, which contain the expression modulants for the protein, the bacterial host, the induction, and the culture conditions. I just want to highlight that it's important to know that sometimes a high production yield imply a poor functionality. Functionality is directly dependent on the protein folding of the structure of the protein. This is naturally found as a homotetramer, which is formed by 4 independent channels, which tend to associate. When these channels, with the channels get denaturated, they lost its structure and the functionality is lost. Also, as an important part of the external domains of the protein are highly hydrophobic, we need to solubilize it and extract them by the use of detergents. However, despite the use of detergents, it is known that the most part of the produced protein are in the form of inclusion bodies, which is an aggregated form, but sometimes the inclusion bodies can contain functional proteins, but it's a challenge to recover this protein from this aggregated form by the use of chaotropic agents. The aquaporin reconstitution process includes the strategies we need to use to stabilize this protein in a reconstitution matrix to form the biomimetic layer of the membrane. This matrix usually is composed by a vesicle composed by lipids or ADA 3-block copolymers. In general, liposomes show a higher incorporation efficiency because lipids have more affinity with the proteins. They tend to form more homogeneous vesicles and forms a more selective barrier. On the other hand, polymersomes forms a more stable and flexible structure. And as you can see in the previous presentation, they have the option to have more modifiable properties. Also, this structure can protect the external domains of the protein. The principal method that has been used to monitor the reconstitution efficiency is the stop flow light scattering monitoring. This method consists in submit the vesicles to a hydrosmolarity environment to induce the vesicle shrinkage. However, this response is dependent on multiple factors, not only the reconstitution efficiency, but also in the protein functionality, vesicle composition, size distribution, presence of defects on the vesicles, and salt concentration. So it's important to consider this factor when we want to extrapolate these results to different conditions. Also, I want to mention that vesicle defects can be produced by the presence of detergents when they are added in excess or when the removal of these detergents is not complete. So that's why it's interesting to consider some detergent-free strategies that could avoid these problems. Now, the immobilization step consists in other strategies we use to adhere the vesicles into the porous substrate to form the biomimetic layer. This includes both the functionalization of the porous substrate and vesicles in order to increase this affinity, or the covering of the biomimetic layer in order to protect it, or to create a more dense superficial rejection layer. I'm not going to talk too deep about this step because until today I still haven't had a chance to work with it, but it's important to monitor the vesicle size, distribution, composition, and the physical and chemical properties of the porous support. Now I'm going to show some preliminary results. Well, in brief, some methods after we define a proper gene of the protein, we transform it an E. coli strain and define the culture and induction condition. The crude extract was submitted to low-speed centrifugation in order to separate the inclusion bodies from the low-speed supernanon, and then this was submitted to two high-speed centrifugation or ultracentrifugation in order to isolate the membrane fraction and obtain the protein extract, which was purified by immobilizing metal affinity chromatography. Then the aquaporin extract, its purity was monitored by size exclusion chromatography and SDA page, and the presence of aggregates was monitored by dynamic light scattering. Also, we evaluated the possibility of avoid the ultracentrifugation step by purifying directly the low-speed supernanon. For the reconstitution, liposomes were elaborated by the film rehydration method. Then these liposomes were destabilized by the use of the detergent OG, octyl glucoside. and it was monitored by optical density, dynamic light scattering, and sub-flow measurements. Finally, the aquaporins were mixed with these destabilized liposomes, and the samples were incubated with biobeds in order to remove the detergent and form the proteoliposomes, and until they are only be able to monitor this by DLS. Now, for this IMAG chromatograph, we can see the importance to modulate the imidazole gradient because it allowed us to separate the non-specific constituents from the purified aquaporin. This is important because sometimes the simple wash or the batch mode, it's not enough to remove all the non-specific constituents. As we can see here, the protein is relatively pure in a homotetrameric form. Also, I want to highlight that these samples were submitted to 8 molar of urea, which is a very strong and denaturant chaotropic agent. So as we can keep the structure stable of our protein, it allowed us to open us the possibility to recover the protein from more protein from the inclusion bodies. Now, in this size exclusion chromatograph, we can see the profiles of the samples with and without the ultracentrifugation step. As we can see here, this step can be avoided without affecting the purity level of the protein. Here, we can see the, in this figure, we can see the profile of a sample after passing through IMAG and a simple centrifugal filter, which ensure a purified protein with no aggregation, as we can see here in this DLS graph. Now, for the detergent stabilization, we can see an optical density, the optical density of different concentration of liposomes when they are submitted to different concentration of detergent. And this is useful because it allowed us to know the point where the detergent molecules saturate completely the liposomes and where the liposomes get completely solubilized. This was also contrasted by this DLS graph, where we can see how the size distribution of the liposomes are affected by the detergent when the liposomes get saturated, when they get solubilized, and when the signal is completely domained by detergent micelles. Finally, as we can see here, the size distribution of the liposomes when they get saturated and solubilized, and then when the detergent is removed, we can see that the saturated liposomes, proteoliposomes, sorry, did not lose significantly their size distribution. However, in this case, when the liposomes get solubilized, the proteoliposomes tend to reassemble, but in a non-homogeneous form, so it's affecting to the structure of the vesicles. Also here in this subflow kinetics, we can see that the reassembled liposomes show an opposite behaviors compared to the liposomes without detergent or the saturated and after we remove the detergent of these saturated liposomes. Now, for the conclusions, ADA fabrication process can still be optimized from each step. Ultracentrifugation step can be avoided without diminishing the purity grade of the protein, and detergent concentration has a significant impact on final vesicle size distribution and permeation capacity, even without aquaporin incorporation. Now, I just want to acknowledge the University of Concepcion, the Catholic University of Chile, and the National Agency of Research and Development for funding my PhD program. That's all I want to tell you. Thank you.
Okay, thank you, Angelo, for your nice presentation. So I'm wondering there is any question for you. Okay. Yeah. So I have a question for you, Angelo. You know, for aquaporin, you know, it's a very promising technology. Yes. However, you know, in the real water or the wastewater matrix, it contains a lot of pollutants. It might cause the inactivation of the aquaporin. So I'd like to hear your comments on this.
Sorry, I didn't get the final part. Could you please repeat the answer, please?
Okay, so for aquaporin, it's very useful. I'm wondering, the many pollutants in water or wastewater may cause the damage or kind of inactivation of the aquaporin during their real applications. So I'd like to hear your comments on this. Thank you.
Mm-hmm. Yeah. Well, that's why to solve, proteins are a little bit delicate, but that's why it's needed to sometimes it depends on the application, but when there's some pollutants, it's needed to apply a covering over the biomimetic layer. The idea of this, it's like to make a small like a filtration, like sometimes like to form a dense polymeric layer, and then the idea of the biomimetic layer under this first layer is to create preferential paths for water. The idea of this is like protect the biomimetic layer from the direct path of these pollutants, which could affect its structure.
Okay, thank you. Thank you once again for your nice talk. Okay, let's move on to our next speaker. It's also the last speaker of this session. It's Dr. Xinglong Ma from Beijing Institute of Technology, China. Today, he will talk about the characteristics of salt accumulation effects on interfacial evaporation in superhydrophilic membranous wick. Okay, Dr. Ma, please.
Okay. Hey, hello. Oh, hello. Can you hear me? Can you hear me?
Yes.
Hey, okay. Time overruns, so I will speak quickly. Okay. This is Xinglong speaking. My topic is characteristics of salt accumulation affecting on interfacial evaporation in superhydrophilic membranous wick. The content contains 5 parts. Now, I should do my introduction. I'm a new faculty in School of Mechanical Engineering, Beijing Institute of Technology. My major is engineering thermophysics and solar technology, including solar concentrators, solar desalinations with humidification and dehumidification, solar stills. All these methods are thermal desalination. I knew this. The theme of this conference is desalination technology with membrane. So I have searched this technology about China, as we can see. We know China has a long coastline, and there has abundant seawater with low salinity. So I think this is a benefit for membrane desalination. However, as we can see, the west and the north areas of China, there has abundant solar energy, and correspondingly, most of these areas lacks of water. We can see the right fingers in Shanxi, Gansu, and Ningxia. These provinces, they have the water resources are always lower than the average global values. And the worst thing is most of underground water is brackish water. So combined with the solar energy, the thermal desalination technology is required in China. What I'm talking about is a hot point in thermal desalination technology. It's very close to membrane desalination. We call it interfacial evaporation. And the figure A shows we can if we put a special material on the surface of the water, and the water will penetrate into the material, and if the solar heat the surface of the material, the seawater can also be heated and will evaporate. The fingers B to D shows different types of this kind of thermal desalinations. This seems very perfect, but of course, it's not perfect. We can also find we can find some problems in this technology. Here shows the flow chart with the feedback. As we can see, the seawater flows along single direction and a dead end. With evaporation going on, the salinity of the water near the evaporating interface would rise, and finally it will crystallize. The salt crystal will prevent the penetration of seawater. One researcher showed the accumulation of salt will decrease freshwater productivity by 40% more. It shows in right fingers. However, this unfavorable circulation seems not exactly right. I mean, we have found salt accumulation has different influence during the scaling. So to validate this question, we have designed the experiment to test it. The experiment contains two groups, as the finger shows. A shows the experimental group. We use siphonage to construct a continuous flow in the inside the membranous wick. And B shows the dead end type. It's a traditional interfacial evaporation. First, we chose polyester fiber as the hydrophilic material. The figure shows the water absorption of the polyester fiber. We can see it has the capillary height of the polyester fiber is about 150 millimeters. It's better than PAV sponge and other wood fibers. Also, we try to construct a siphonage flow. This fingers this is a later experiment. We try to test the siphonage flow. The interesting thing is that the flow rate is obviously changing with the length and height. So that means we can control the flow rate easily. Okay, then we set up an experiment according to the above test. We set two groups with one control group and one experimental group. The control group, the water can be flow continuously. Here shows the results and the discussion. The first test, we use the normal seawater with salinity of 3.51%. As we can see, when heating time is about 150 minutes, the temperature obviously separate. When time goes to 300 minutes, temperature of experimental, this is control group. The temperature of the control group is 2 degrees more higher than the experimental group. Look at the right finger. It shows the evaporation rate of control group is higher at the beginning. Then it became slower, and the evaporation of experimental group is always keep line increasing. Then we set another test. We use the high salinity seawater to test again, and the same phenomenon can be observed. Because of salinity is high, the scaling is also become earlier and faster. Then we choose the second test as an example to make a explanation. As we can see, for the dead end group, the photo shows in 15 minutes. The photo shows in 15 minutes. It's only a slight crystallization, and the evaporation is improved. This is because the salt has large thermal conductivity, which makes the temperature of the interfacial higher. However, when salt accumulation more, like photos of 100 minutes to 150 minutes, the salt crystal will prevent penetration of seawater. In this case, even though the temperature is higher, the evaporation rate is becomes lower. So we can make a summary as follows. So how to balance the salt accumulation and evaporation rate? It can say that salt crystals in the materials does not completely hinder water penetration and evaporation. Actually, the slight crystallization is benefit for the evaporation due to salt crystals improve the interfacial thermal conductivity and increase the temperature of the evaporation interface. Thus accelerate evaporation rate. By contrast, a heavy crystallization would form a hard salt shell that covers on the surface of the membranous ring. In this case, the evaporation rate will be obviously weakened. So if the heat balance can be controlled perfectly, I think the salt accumulation is positive to evaporation. Okay, my presentation is over. Thanks for chair one.
Okay, thank you for your nice presentation. Is there any question? I did not see the Q&A window.
Okay.
No questions?
Yeah, because my my topic is about thermal desalination. It something, yeah, it seems a little different than membrane.
Yeah, I have a question for you.
Okay.
Rama. You know, for the thermal desalination technique is also a hot topic. I know that many groups are involved in such kind of topic. So I'm wondering, you know, for the materials that you prepared, the advantage of it compared to the literature that you know, a lot of researchers have investigated.
Mhm.
Yeah. Okay, thank you.
Okay, thank you.
Okay.
Yeah. Can you hear me? Oh, sorry.
Yeah, I can hear you. You know, I'd like to hear your comment. No comment on this. I mean, the advantage of
Oh.
your materials compared to the other materials reported in literature.
Yeah, of course. And something
Yeah.
like I have mentioned in this presentation, it's like a
Mhm.
PAV sponge. You know, it's a industrial materials. It's very cost effective. And other something like wood fiber. Wood, we know it has a hydrophilic materials. Something like paper issues and some bamboos. These are we know it's very ecological and environmental beneficial.
Okay.
Thank you. Mhm.
Okay. Yeah, thank you once again for your
Okay.
okay presentation. Okay, ladies and gentlemen, you know, with this, I'd like to wrap up this session of the session 5B. You know, we have heard of a lot of interesting work, you know, such as the PEI nanofiltration membrane, and also the isoporous, you know, nanofiltration membrane, and also some new perspectives for the biomimetic membrane fabrication, and also the thermal evaporation for seawater desalination in this session. So I'd like to thank all of the presenters for their interesting talk. And also I'd like to thank all of the participants for you know, attending this session. Thank you very much. Thank you. Bye-bye.
Okay, thank you. Bye-bye.
Bye-bye. Thank you.
Bye-bye. Bye-bye. Thank you.
Bye.
Bye. Thank you.
Bye-bye.
How to